In this video, we're going to talk about the different types of solutions you have when solving a system of linear equations. Again, when we talk about systems, what we're really talking about are two or more linear equations. Now, if we think of this graphically, a solution is the point where my two lines intersect. And I could graph both of them, look at the intersection point, and see what x and y values we have. Algebraically, when we're talking about a system of linear equations, we're talking about the ordered pair that satisfies both equations. In other words, if I took this point xy and plugged it into either of these linear equations, I would end up with a true statement. So here I've worked out a problem algebraically. I used the elimination method, canceled the y's, and I actually got a value for x. In fact, I found out that x equals positive 4. When I substitute that value into either one of these equations, I chose the second, I can solve and find a value for y. And what this tells me is that if I was to graph these two lines, they would intersect at the point 4, 9. The next scenario is that we have a system that has no solution. If we have a system that has no solution, essentially what that means is our two lines will never intersect. In other words, they're parallel. Algebraically, what would happen is I would have a pair of equations. I would have a system of linear equations. Again, I'm using the elimination method. My y's cancel out when I add my equations together, and I have 0x equals 4, which means 0 equals 4. Well, clearly that's false, and what that tells me, because all of my variables dropped out, and I was left with a false statement, that tells me there is no solution. In other words, there is no ordered pair that will satisfy both equations at the same time. And that makes sense when we think about it graphically because the lines never cross. There isn't going to be a point that the two lines have in common. The last scenario is when we have infinitely many solutions. In this scenario, when we go to graph our two lines, what we find is that the two lines are laying right on top of each other. In other words, when we're looking for the point of intersection, they're effectively the same line, different equations for the same line, and so they are always touching. We would say there are infinitely many solutions. Algebraically, what that's going to look like, and I did substitution in this case. I plugged the second equation into the first equation. What we find, we lose our variables just like before, only this time I'm left with 6 equals 6, which clearly is a true statement. And because all of my variables dropped out, I was left with a true statement. We can say that there are infinitely many solutions. And if you want to be more specific, and I encourage you to be more specific, we can write it up in set builder notation, which says, I'm going to translate this, when you see these little squiggly braces here, that means we're writing a set of answers. The set of all ordered pairs x, y, this vertical line here means such that, and then you state a rule. In this case, we're talking about all ordered pairs that satisfy this equation, or all ordered pairs that make this equation true. So again, our three scenarios: one solution, the lines cross at one point. Algebraically, you get an x value and a y value. No solution, your lines never cross, they're parallel. Algebraically, your variables fall out, you're left with a false statement. Or infinitely many solutions, your lines are always touching. Algebraically, your variables fall out, you're left with a true statement. And then we have this language: consistent, independent, inconsistent, independent, consistent, dependent. I'd like you to think of this terminology. We're going to look at consistent and inconsistent. I always think of consistent as a solution exists. Well, we can see that a solution exists if there's one solution or infinitely many solutions. Those systems, those types of systems are considered consistent because there is a solution. Independent means my two lines are unique. So I look at this, my two lines, they're different lines. I look at the no solution case, my two lines, they're different lines. I look at the dependent, these two lines are the same. So we could think of independent versus dependent in this way, where independent means that our two lines are different. And that's going to wrap up the different types of solutions you have for solving systems of linear equations. Thanks so much and have a great day.